Good afternoon. Let me take this opportunity to welcome you to day 2 of the NLP Summit. My name is Dave Kincaid, and I'm a data scientist at IDEX Laboratories. IDEX is a biotechnology company in the animal healthcare space. In addition to manufacturing in-clinic diagnostic instrument and running a global reference laboratory network, we also provide electronic medical record systems to veterinary clinics and hospitals. These diagnostic systems and EMR systems generate a lot of clinical data in both structured and unstructured forms. We already heavily use Spark to process tens of terabytes of clinical data, so when we started working on applying NLP to the unstructured clinical notes, we naturally put John Snow Lab's Spark NLP at the top of the list. However, our data science team is primarily an R shop, and Spark NLP supported Python, Scala, and Java. So this led me to finding a way to use R and Spark NLP together. I'm excited to be able to share this result of my work with you today. During the next 20 minutes or so, I'll take you briefly through what R is, how we can use Spark and R together, what Spark NLP is, how we combine Spark, R, and Spark NLP. I'll assume that by this point you're familiar enough with Spark NLP that I won't spend too much time on it by itself. I'll then show you several code examples of what it looks like to use R to drive Spark NLP. Hopefully by the end, you'll understand enough about R, Spark, and Spark NLP to give it a try yourself. For those of you who are not aware of what R is a programming language, and it's a programming language that's aimed mostly at statistical computing, data processing, graphics, and data science. It originated in the early 1990s as a free implementation of the S programming language. The initial public release was in 1995, and since then, it's grown in popularity. It sits at number 9 on the TOEIC Programming Languages Index, and that's up from number 19 in September of last year. Along with Python, it is widely used in data science, and its capabilities grow by the day through its very vibrant community, which develops thousands of packages implementing every manner of application. From the earliest releases of Spark, there has been an R API. The official Apache release of Spark includes the package Spark R. This package offers a robust interface from R to Spark, but uses very Python-like syntax. In recent years, a popular framework for efficiently working with data in R has emerged called the tidyverse. At the center of this tidyverse is a package called dplyr. Dplyr offers a common syntax and a set of functions that can be used against local data or data residing in remote databases, so that the same source code can be easily used against a CSV file or SQL remote databases by simply changing out the backend connection that's used. One dplyr backend that can be used with Spark emerged from this. That package is called sparklyr and was built and is maintained by RStudio. We can compare the syntax of Spark R and sparklyr. Here, I'm showing you the same example in Spark R on the left and sparklyr on the right. This example will work with a fictional CSV file containing sales information. We want to create a summary from this sales data containing the total sales for each of our sales reps. So here in the first line, we connect to Spark. Then we read in the sales data from the CSV file into a Spark data frame. Next, a variable is created containing only the rows for my sales using the filter function. The next line creates a new column in the data frame called sales. Spark R does this using syntax similar to base R. And on the right, sparklyr uses the mutate function. So this simply calculates the total price of the sale by multiplying the price and quantity in each row and creating a new column called sales. The final chunk of 4 lines of code calculates total sales for each sales rep using the group by and summarize functions, and then sorts the data frame in descending order by each sales rep's total sales using the arrange function. It's important to note that all the operations here are taking place inside of Spark and not inside of the R local runtime. So in terms of number of lines of code, we can see there really isn't much difference here. Function names are nearly identical. The sparklyr code is a little bit cleaner in the expressions for specifying data frame columns that were being worked on, but overall there's not much difference. So you may be asking yourself, what's the difference between these two examples? So the main difference between these two examples, despite how similar they look, is that the sparklyr code on the right could quickly be changed to read from either a local CSV or from a SQL database, simply by removing the first line of code that sets up the Spark connection and replacing the second line with a call to something like read_CSV or tibble to connect to a remote database. All the rest of this code would stay the same. The SparkR code on the left will only work in Spark. So one other advantage of sparklyr is its extension mechanism. So it's relatively easy to extend sparklyr to implement some additional Spark functionality. Here I list a few examples, like an extension to read in SAS data in parallel into Spark, or one to use H2O machine learning algorithms against Spark data frames, or the sparklyr.flint extension that implements the Flint time series library functionalities, or GeoSpark, which brings geographic functionality to Spark through R. And there are many more extensions. To this point, I've been talking about generic R and Spark integration. So what about NLP? You're all probably quite familiar by this point with what Spark NLP is and what it offers us. Briefly, for those who may be new to it, Spark NLP is a state-of-the-art natural language processing library that gives us the ability to do NLP in production at scale. Obviously, it runs inside of Apache Spark, which means it leverages all of the distributed computing capabilities of that platform. It can be used for multiple languages, including Python, Scala, and Java. And as you're going to see very shortly, R now as well. It contains a very complete set of NLP tools, including tokenizers, stemmers, part-of-speech tagging, word embeddings, text classification, sentiment detection, named entity recognition, and many more. It also very seamlessly integrates with Spark ML functions. For our particular use case, we needed a framework and a system that can scale to billions of documents. This all leads me up to the point of what I wanted to share with you today. Last year, while we were investigating NLP tools and became very interested in Spark NLP for its broad functionality and the fact that it runs in Spark, I approached the RStudio team to see if they knew of an existing sparklyr extension for Spark NLP. In a case of be careful what you wish for, they told me there wasn't, but they could certainly help me to create one. So with a lot of excellent support from Kevin Kuo and Javier Lurashki at RStudio, I began my journey into the world of sparklyr extensions and Spark NLP. I was new to both Spark NLP and these extensions. While I was very fluid in sparklyr, I'd never tried to create an extension. Nevertheless, we needed the functionality, so I dove in. The result is what I'm showing you here today. I've created a sparklyr extension, appropriately named Spark NLP, that brings all the functionality of Spark NLP to R. This extension covers all of the Spark NLP unlicensed functionality, including annotators, transformers, pipelines, training, and utilities. It's available from the RSpark GitHub site and includes some sample R notebooks. Being able to have our data science team work in a language that they're comfortable in, like R, to experiment, develop, train, and test models, serialize those models, and then be able to easily read them back into our Java-based production environment is exactly what we were looking for. So Spark NLP, and R gives us exactly this. The extension's not yet in the CRAN global package repository, but it's easily installed in R right from the GitHub repository using your favorite installation method like remotes or pacman. Simply run one of the two commands shown on this slide and the package will be installed in your local R system. The master branch, which both of these functions default to pulling from, always contains the latest stable release of the package. If you're brave, you can try out the dev branch, which will include any work in progress, but I warn you that that code may or may not work, may or may not have bugs. Before we dive into some example code, a quick note about syntax conventions in sparklyr. Functions in sparklyr all have a prefix according to what functionality they target. For example, functions like reading data and connecting start with spark underscore. Functions that work on data frames will start with SDF underscore. Machine learning functions start with ML underscore, and so on. So following this convention, all of the functionality in this new Spark NLP package starts, not surprisingly, with NLP underscore. So let's now take a look at some code. So some preliminaries to get out of the way first. The first part of using the package is to load it in using a library command or something like pacman pload if you prefer, and then to connect to Spark. So here we use the functions spark underscore config and spark underscore connect from the sparklyr proper package to configure and create our Spark session. In this code, I'm using a default configuration with the exception of increasing the driver memory to 16 gig and turning off the Spark console log messages. Then we launch a local instance of Spark using all cores and our configuration. In the slides that follow, you'll see the variable SC. So that is our Spark connection with all of its parameters. We pass that variable into each one of the NLP functions. So here's our first real code snippet. This one shows how easy it is to use one of Spark NLP's pre-trained pipelines. In this case, we're going to use the explain document DL pipeline. After creating a test document variable I'll call test.doc, we simply need to call the NLP pre-trained pipeline function, passing in our Spark connection, the pre-trained pipeline name, and the language we want to use. Once we have that pipeline, we can start using it with the NLP underscore annotate function simply by passing in any documents we want to annotate. After we've done that, we can look at the resulting data frame with the Spark NLP annotations and see the output from each of the annotators in the pipeline, such as the tokenizer, the lemmatizer, the stemmer, the spelling corrector, and the named entity recognizer annotator. You should notice that the token, PERSN, which was misspelled, has been spell corrected to person, and also that the token Peter was identified by the NER annotator as a person entity. This second example is creating a custom pipeline using Spark NLP pre-trained models. So this is demonstrating both how to create a custom pipeline as well as use Spark NLP's pre-trained models. Here we create 4 annotators using the functions in the Spark NLP package. For each function that creates an annotator, we pass in the Spark connection, define the input column names for the annotator and the output column name, along with any other parameters we wish to set for that annotator. We first create the document assembler annotator, specifying the input column to use as text, and the output of the annotator should go into a column named document. Next, we create a tokenizer annotator. This one will use the document column as input and will output the tokens to a column named token. Next, we create an annotator that will generate the glove word embeddings for our tokens. Here we use a Spark NLP pre-trained embeddings model called glove underscore 100D. And we specify the input columns that were to be embedded as document and token and tell it to write the embeddings to an output column named embeddings. Finally, we created an NER deep learning annotator using the Spark NLP pre-trained model named NER underscore DL. For this one, we specify input columns of document, token, and embeddings, which are required by the NER annotator. And we tell it to output its NER annotations to a column named NER. Finally, we take these 4 Spark NLP annotators we've created and we assemble a pipeline. You'll notice that the function we use to do this is ML underscore pipeline. It has that ML underscore prefix, so you can see this is actually building a Spark ML pipeline. Once the pipeline is created, it's fit using ML underscore fit function, which in this case actually doesn't do anything except turn the pipeline into a fitted pipeline type, since there's nothing in the pipeline that needs to be fit or trained. So for performance, I just give it an empty data frame. Then we can use ML_transform to run the fit pipeline against any data frame, as long as it has a column named text that contains the documents to be processed. In this example, I have read in a newswire corpus into the data frame named news_df. This data frame contains a single column named text, where each row contains a single news article. Now we have a data frame named result that contains columns created by each of these annotators in the pipeline. For example, the tokenizer annotator created a column named token. The NER annotator created a column named NER. These are the names we specified when we created the annotator in the previous slide. The values in each of these columns are arrays of NLP annotation objects from Spark NLP. Each of these objects contains 6 fields: annotator type, beginning index, ending index, result, metadata, and embeddings. In the example here, I'm simply exploding out the result element from each of these objects in the token and NER columns. So if we look at the tokens that are produced, we can see that certain tokens have been given organization NER tags. The tokens Turner and Newell, in fact, were identified by the NER annotator as a single organization named entity. The final code example I'm going to show is an example of training your own NER model using Spark NLP. Here we see a couple of new functions. The first one at the top, called NLP co-NLL read dataset, reads in a text file that's been formatted in the co-NLL 2003 NER tag format that's required by Spark NLP's named entity recognizer annotator. This function creates a Spark data frame containing the text, tokens of the text, and the NER labels for each token. This is the data frame that we'll use to train our model. The second line uses the pre-trained glove word embeddings model as we saw previously. The NER model we'll use is a deep learning based model from Spark NLP, the NER DL model. This is the third line of code you see, and it contains all the tuning parameters needed to build the deep learning NER model. The input column names are the default names created in the data frame by our call to co-NLL read dataset and by the glove word embeddings annotator. So these are sentence, token, and embeddings. We put together the word embedding annotator and our NER DL model annotator into a Spark ML pipeline as before. And then we simply train the model by calling ML_fit on the pipeline and then passing in a reference to our training data frame. This then will train the NER model using the parameters we specified. Now we can use this trained model to annotate new documents. So here we'll use a test set that's in the co-NLL 2003 format so that we can measure the accuracy of our trained model against a held out data set. So we generate predictions from the NER model using ML_transform, passing in the fit pipeline and the data frame containing our test data set. As you can see, we extract out of the predictions data frame the annotations from our model in the NER column and compare it to the gold label in the label column. Here, each document is a row in the data frame, and each column has been formatted to a JSON string of just the annotation labels for all the tokens in the document. When we glance at this result, we can see the first few tokens in the token column, gold labels in the label column, and our model's predicted labels in the NER column. For display purposes, I truncated each of the JSON values to just 20 characters. But glancing at this and comparing the label and NER columns, we can see that our model did well with the first 2 documents, but not so well on the third, at least looking at the first few tokens. So the package is available now, contains all the functionality up through version 2.5.5 of Spark NLP, plus the bug fixes for 2.6.0. The version of Spark NLP the package is currently using is 2.6.0, but I haven't yet gotten the new 2.6 annotators added. Those are multi-classifier DL, BERT sentence embeddings, and the Yake model. I expect to have those added into the package in the next couple of weeks. I want to reiterate that currently the licensed annotators and models are not implemented in the package. If you start using the package and have any questions or problems, there are a few options for getting support. My preferred option would be to utilize the John Snow Labs Slack server. I am pretty active on there. There isn't a dedicated R channel on there yet, but maybe they'll create one if there's enough demand. The next option would be to open a GitHub issue in the Spark NLP GitHub repo. This is the R Spark GitHub repo. Please don't open a GitHub issue in the John Snow Labs Spark NLP repository. You can also message me on LinkedIn or at my email address. We've been using this package internally at IDEX for several months, and we should have worked out any major bugs, but our workflow may not match yours. So it is possible for there still to be some issues with other workflows. I'd love to hear about your experiences in using Spark NLP with R. I hope you found this interesting and useful. If you're an R user and have been wanting to try Spark NLP, this is your chance. In closing, let me mention that we are hiring. If you're interested in working with really interesting animal health data and NLP, please reach out. Thank you.